Today we're going to kind of put the so last time we had kind of had this procedure for finding these zeros that are also x-intercepts, right? We've used the term zero and x-intercept fairly interchangeably. They're not quite the same thing. So we're actually going to extend that procedure a little bit today so that we can actually find all the zeros and not just all the x-intercepts. So let's just start by clarifying the difference between, like, when we talk about the zero for a function, the x-intercept for a function, because the two are like related. So 0 versus x-intercept. All x-intercepts are zeros. Period. Now, what's the catch here? Is that some x-intercepts count as more than one zero. So for example, let's say we have the polynomial x squared plus 6x plus 9. If I want to find the zeros for that, I set it equal to 0. And I solve. You could solve this by factoring. The two things that multiply to give you 9 and add to give us 6 are x plus 3 and x plus 3. So when I solve this, I get the solution x equals -3 twice. Do you guys remember what it's called when we get the same solution more than once like this? We had a name for this. We mentioned it earlier. This is a multiplicity, right? In this case, this would be multiplicity 2 because we get the answer twice. So what we have is 2 zeros those zeros being -3, which we're counting twice. But the x-intercept we have is just 1. Everybody's okay with that? So far, so good? Okay. But like, big whoop, Mr. Kulik, like, that x, so what? The extra 0 is still an x-intercept, so like, what are we making a big deal about this for? Well, not all zeros are x-intercepts. How the heck is that happening, Mr. Kulik? Well, consider the following. Let's say we have x squared plus x plus 1. Oh, polynomial. Okay, so that's our polynomial. if I try to solve that, or if I go to find the zeros, excuse me, so I set it equal to 0 and then try to solve, can I factor that? It's quadratic, but can I factor it? There's no leading coefficient or greatest common factor to suck off. Yeah, or is there two numbers that multiply to give us 1 and add to give us 1? No. So what should we do? Still do the quadratic formula, right? Right, we can always do that to solve a quadratic. So I got -1 plus or minus square root of -3 over 2. Who says uh-oh? All of you should. Uh-oh. Why? Yeah, we have that negative underneath the square root. Oh no! What did that mean? Means we get an imaginary result. So my zeros here would be -1 plus or minus I square root 3 over 2. Keep in mind that's two zeros because of the plus and minus. Maybe we'll write it as two separate things just to really hammer that home. Right? Two zeros. Now if I were graphing those, do those appear on the x-axis? No, man. Why not? Well, it's not a real number, right? We don't have any imaginary stuff on the x-axis. The x-axis only has real numbers on it. None. Okay? So when we talk about x-intercepts, we're not worried about multiplicities. And we're not worried about imaginary things. When we talk about zeros, though, we are concerned with the multiplicities and we are concerned about the imaginary pieces. Okay? So we've used the two terms x-intercepts and zeros pretty interchangeably, and to some extent, up until this point, they're interchangeable enough. But here we're going to start considering imaginary possibilities, so I'm going to switch and start talking all zeros and no more x-intercepts because, well, it's important to be specific. So you guys cool with the similarity and difference between the two? Okay. All right. So two tools. Well, actually, we're going to get three tools. I take that back. Two tools today to kind of help us out with this. So the first one is a theorem. It's called the fundamental theorem of algebra. I'm just going to abbreviate that as FTA for fundamental theorem of algebra. And this one's pretty powerful. It tells us that a polynomial of degree n will have exactly n complex zeros That is, if we are counting our multiplicities. One word in here worth double checking that we understand the difference of when we say complex. Does that just mean really complicated? No, what does complex mean in math class? So the complex numbers are what we're talking about here. The complex numbers is a set of numbers. The complex numbers are of the form a plus bi, where a and b are real numbers and I is the imaginary number that's equal to the square root of -1. So this basically means the complex numbers include things that are real numbers, things that are imaginary numbers, and things that are like a combination of real and imaginary parts. So everything that we've seen up to this point counts as a complex number. Cool? Again, you guys remembered that. Sometimes the words escape us at 7:45 on a Wednesday morning during Irish week. You know?
The game starts. Sorry, it's off top.
Yeah, it's after the 4 classes.
Okay.
So I don't know, like 4 hours from now.
Okay.
I think all the classes are about an hour.
Okay.
We'll do some luncheon before that. I think you do 4 classes, then their lunch.
It's the 4th hour replacing the 3rd and the 3rd replacing the 4th today.
Well, I don't even remember. I don't know. We'll figure it out. All right. So the next piece that we have is another theorem. This theorem is called the complex conjugates theorem. So this says that a polynomial with real coefficients actually we should say for a polynomial with real coefficients. If a plus bi is a 0, so is a minus bi. As a reminder here, so we have this is called the complex conjugates theorem. When we say conjugate in mathematics, we're talking about things like a plus bi and a minus bi are conjugates, where they have the same thing except they have a different sign between them. Those are conjugate pairs. So for example, something we might use this to do is so if we want to write a polynomial with real coefficients, it has the zeros 1, -3, and 1 plus I root 2. This is similar to the problems that we did on 13 and 14. So we're just going to take each of these zeros and turn them into factors. But when we get to this one with the complex 0, we know we're also going to need its conjugate. If we don't include its conjugate, we won't get the real coefficients that were desired. And when I subtract the complex number over, I like to just take the whole thing and put it in a parenthesis with the negative sign out front of it. It makes the next step, I think, a little bit easier for me. and I'll show you why in a moment. Is everybody okay with what I've done so far? All right. So I have these 4 equations here, right? What I'm going to do is I'm going to multiply these 4 equations together. That means I'm going to multiply all of the left sides together, and then I'm going to multiply all the right sides together. Yeah, Joe.
Just a question for you, I guess. So you know how in the area, like you highlighted green stuff, when it's x minus and then x minus as well for both of those equations. How come on the first one it's not x plus? Is it always x minus?
Well, I'm taking this as one thing and I'm subtracting it over to the other side.
Oh.
So I just put the parenthesis around it and the minus in front. And I'm doing that because on this step, it actually is going to make the arithmetic a little bit easier to think about it that way, rather than subtracting the 1 over and then subtracting the I root 2 over.
Okay.
It means less negative signs, and I think it's going to make our lives a little bit easier in the future, which is why I'm doing it that way. It's not wrong to do it one piece at a time, but I think it makes it more inconvenient in the future.
Sounds good.
But totally reasonable question. Everybody's cool so far? Okay. What I'm left to do now is to FOIL everything out. I'm going to FOIL these 2 pieces together, and then I'm going to FOIL these 2 pieces together. You'd always want to FOIL the conjugate pairs in the same group, because in doing so, all the i's and everything are going to drop out of there, and you'll get a nice result. So I did that first foiling there quickly in my head. I hope everybody's okay with that. You could FOIL it out on your own to double check that. The next one, though, I'm going to go slowly through so you guys can see what I'm doing, because it gets a little bit complicated here. So x times x, that's x squared. And then I'm going to do x times that whole thing. So I'm going to have the negative sign. I'm going to put the x in front. And then I'm going to write the parenthesis. And I'm going to do the same thing here. And you're seeing now maybe why Mr. Kulik wanted to just leave it in one parenthesis, because it makes the foiling a lot simpler if I'm thinking about it that way. And I'll multiply these together. Since both of them are negative, I get a positive. And then I have just the I plus, or 1 plus I root 2 and 1 minus I root 2. Everybody's okay with the foiling that I did there? All right. We got a lot of cleanup to do on this one. I'm going to start by distributing the x's through. Everybody's okay there? Leo?
When you like distribute the I plus imaginary number, do you take the negative and drop it?
Yeah. Yeah, so on this one I had negative times negative. That's why I have a positive there.
Yeah.
And then here I have the negative times the positive. Ooh, I forgot the negative there. Thanks, buddy. Buddy. That's why I'm getting the negative there. Cool. This last set of parentheses then, I have to FOIL that again. Right? Do you notice anything about that FOIL problem though? Isn't that a difference of 2 squares? A plus b times a minus b. Do you guys see that? What does that do for me if I'm foiling? it wicked shortens the foiling up because I just have 1 squared. That's a squared minus b squared. Right? I don't actually have to do all the foiling. I can just shortcut it. Is everybody okay with the shortcut I did there? You could foil it out by hand also. Not wrong to do that, but like this is the benefit of like leaving everything in parentheses like I did. Grace? Absolutely. All right, let's combine some stuff together now and simplify some more. So I have a positive I root 2x and I have a negative I root 2x. Those guys just cancel out. That's pretty choice. 1 squared is just 1. And then I root 2 squared. Well, when I do I squared, and then I have root 2 squared. Everybody's okay with that? Root 2 squared is just 2. And what's I squared? Do you guys remember that? Okay, so remember I was the square root of -1. So I squared is just -1. So this whole thing just turns into -2. Okay. So we have x squared. Then I have minus x, or minus 2x, excuse me. And then we have, let's see, we have 1, and then minus a -2. So that would be 3. Exactly. And now I just foil these two together, and then I'm done. So I just doodly doos that. That should be a 4. So I have x to the 4th. Then I have cubed. So those got rid of each other. That's cool with me. Squared. So I have 2x squared. And then I have greens. Those cancel out. I have +9. Oh, great googly moogly. Look at the mistake that Mr. Kulik made. Oh, it's so early. So guess what? Bunch of stuff is wrong. I know. I'm sad too. Those guys are all negative now. Oops. This guy's positive. All right, let's try this again. Oh, Mr. Kulik. I don't know. I don't have any excuses for you guys. I'm better than that. Yeah, it is 8 a.m. That's my excuse. Sheesh. That one's right, though. So what's the worst part about this? The multiplying. Which is like, yuck. It's just tedious, right? There's a lot of symbols to keep track of. but realistically, all we're talking about is a bunch of foiling. It's just a lot of stuff to keep track of. It takes a little bit of time. It's pretty tedious. The actual algebra part, where we created this guy, was pretty easy, though. Foiling that guy out was a pain in the tuchus. Yes, sir.
When the test comes around, can we bring like highlighters so we stay organized?
Absolutely, yeah. You want to bring a bunch of colors, you want to color code things, highlight things, yeah, no problem.
Probably be easier for the foiling.
Yeah, keeping track of what's going on, I get it. I don't have any problem with that. The easier it is to read for me, the easier it is to grade. So if you better organize, you stay and incentivize. I'm fully incentivized to let that happen.
Sounds good.
All right. Okay. So let's talk about finding all zeros now. Let's return to this synthetic division process. Okay, notice we say all zeros, so we want any multiplicities. We want to list, find, identify those. And if there's imaginary pieces, we want to make sure we find those as well. So we can't just look at the graph and use the x-intercepts, because the x-intercepts aren't going to tell us the multiplicities for sure, and it's not going to tell us the imaginaries ever. So we have to be able to do the synthetic division or use some other algebraic method to do this. All right. According to the fundamental theorem of algebra, I should have exactly 3 zeros. Okay with that? What I'm going to start by is identifying any possible rational zeros. So to do that, I need the things that are of the form P over Q, where P is my factors of 36. So 1, 2, 3, 4, 6, 9, 12, 18, or 36. Oh, Mr. Kulik, there's so many. Yeah, but Q is just 1. So I just have my factors of plus or minus my factors of 36, which isn't great, but it could be worse. All right, to decide which one of these I want to start my synthetic division with, what should I do? We'll look at the graph, because if none of these if none of the x-intercepts correspond to any of these guys, I am up a creek without a paddle. Actually, Mr. Kulik's not. He has other methods that he could use here, but so I see an x-intercept. Yeah, Aaron. Of course. I see an x-intercept. It appears to be at -4. You guys agree with that conclusion? Just for the record here, if I look at my graph and it just looks like a blank screen, what should I do? Yeah, make my window wider, right? How wide would I potentially need to go? -36 to +36 would give me, if it doesn't cross in there, it's just not going to cross. Well, I mean, it could cross, but it won't be a number that could be useful to us. All right.
Why is Q only 1?
So yeah, sure, good question. So the P is the 36, the Q is the leading coefficient,
Okay.
which
As factors in the
correct.
I thought it was the exponent. Factors the exponent.
Oh.
1 and 3.
Yeah, nope, leading coefficient. Good question. We good still? Okay. Let's start setting up our synthetic division. We only have one number to try, so that's pretty righteous. It's a pretty crooked bar, Mr. Kulik. That's still crooked, but less. So we'll just grind through this. But it worked. Right on, dude. So remember, this is my remainder, constant, x coefficient, x squared. So what I have here is really x squared plus 9 should be my other factor. And I'm going to stop here with the synthetic division piece because the other factor that's left is quadratic. And I certainly can solve that without having to do synthetic divisions. And in fact, there's nothing left for me to use synthetic division on anyway, so like, pretty sure this is going to give me some imaginary thing coming out of this. So if I take that x squared plus 9, set it equal to 0, how would we want to solve this guy? It's quadratic. Doesn't factor, dude. You'd have to multiply to give you 9 and add to give you 0. No two numbers are going to do that. What would you do if you can't factor it? You could use the quadratic formula, sure. Remember the quadratic formula for ax squared plus bx plus c equal to 0. X is negative b plus or minus b squared minus 4ac all over 2a. You could do that, absolutely. In this case, what is our value for a, b, and c? 1, 0, and 9, right? So 0 plus or minus 0 squared minus 4 times 1 times 9 all over 2 times 1. So that's going to give me plus or minus root negative 36 over 2. Root of negative 36 is about 9i. 6i. Oy, oy, oy. Right? Square root of 36 is 6. Then the negative gets the I. And then I can reduce that to just being plus or minus 3i. And then if I take this one, obviously, negative 4. So my zeros are negative 4, and then plus or minus 3i. And if you wanted to write them as two separate things like plus 3i and minus 3i is rather than plus or minus, that's fine, whatever. Mr. Kulik is flexible with your communication as long as it's communicating the same thing. What do you think? Not bad. How much time do we have left here? We finish at 8:35, so 12 minutes. I feel like this is an okay place to stop. We're going to just pick up and do some more examples of this process then next time. I'm not going to bother adding anything to or even starting the problem set for next week because we'll just do another day of with some examples and give you some time to work on or start the next part of the problem set. So that feels good to me. So reminder, Sunday's problem set is going to be 13 to 14, 20 to 31, 32 to 35, and worksheet 1. And then what will it be? It would be Monday next week when we meet again. We'll pick up where we left off here, and then finish up this chap. How's that feel? Everybody's okay with that? Hopefully, it's a pretty chill.
Mr. Phillip, can you do an example really quick?
Yeah.
From the worksheet.
Oh, sure.
Do you want me to tell you that we have?
I got the worksheet here. 6. Okay, homie.
Do you use the quadratic formula?
I mean, I'd start by factoring off a greatest common factor. And then I can factor that. Multiplies to give us 16, adds to give 10.
Yeah.
8 and 2, right?
What about the 4y?
Well, that I'm just going to ignore until the end. You good with the factoring?
I can just keep it like that. That's fine.
Well, you want to solve this, right? I think was the directions. So we just apply the zero product property and set each factor equal to 0. Divide by 4. Subtract 8. Subtract 2. So 0, negative 8, negative 2. Does that feel okay?
Yeah.
So make your life easier. Start with that greatest common factor.
Yeah.
Is that what you forgot to do?
Yeah.
Definitely.
I'm going to want to use like the quadratic formula on other problems.
You could possibly need to use that, yes. And in fact, at this step, you could have, instead of factoring the y squared plus 10y plus 16, is you could elect to use the quadratic formula there, and that would be fine. Yeah. To me, since the leading coefficient is 1, I'm just going to try to factor it because I'm really good at that, and it's going to take less time than trying to grind through the quadratic formula for me. But like, whatever your comfort level is, I'm not going to argue with it. It's a valid method. You could certainly do that. That feel good, Leo? Yeah, of course, my man. All right.